So now that we've learned about possibilities, that is, the permutations and combinations of all the possibilities of outcomes, now let's start talking about probability. So, and for starters, we'll look at a discrete probability. And so by the end of this video, you should be able to compute the probability, little p, of an outcome or a success, if you want to call it that, given some very simple assumptions about the system. And then the second learning objective is that you'll be able to use the binomial distribution to compute the probability of an arbitrary number of outcomes, R outcomes, or R successes, given n tries, given that the probability of a single success is little p. So, for example, say we have a coin. So what's the probability of getting a success? Say tails. So probability of tails with one coin flip. Well, we know that there are two sides of a coin. So, and the tail represents one side, so we have one side that's a tail, and there are two possible sides, so we know that little p in this case is equal to 1/2. So what's the so that's a very simple example. And so what would be the probability of drawing one ace from a deck of cards? So we know that the number of decks and cards in a deck is 52, and there are 4 aces in a full deck. So there are 4 possible successes out of a deck of 54. So that's the probability of drawing a single ace out of 52 cards. So in general, the probability of a success, given that there are S successes in the whole system and other possibilities, this is the general solution. And actually, I'm going to use the uppercase n for the number of possibilities in the system. I'm going to use lowercase n for another case, for another meaning. So this is the first learning objective. So given some simple assumptions about our system, you can now compute the probability of a single success. So now what is the probability of a single failure? So if there are S successes in the system, then there are n minus S failures in the population or the system. So the probability of failure is equal to the number of failures, n minus, again, I should use large S here, or sorry, large N. Large N. Probability of failure is n minus S failures in the whole system divided by the number of total outcome possibilities. And so this turns into 1 over n minus S over n, and that's equal to 1 minus S over n, and that's equal to 1 minus the probability of successes. So that's the probability of failure. And so what this is also illustrating is that the sum of probabilities of all possible outcomes is what? What's the sum of the probabilities of all possible outcomes? And if you had the number 1 in your mind, then you got it right. So the sum of all of the probabilities of all possible outcomes is 1. So now let's talk about the binomial distribution. And the example here is, let's say we're doing some exploratory drilling for geothermal heat. And let's say, for example, that the probability that if we drill one hole and the probability of a discovery is 1. So probability of one hole being successful is little p. Okay. So the probability of a failure, if we drill one hole and we find out that the hole is cold, there's cold water instead of hot water, then the probability of failure is 1 minus little p. Okay, so what is the probability of drilling 3 successive holes and getting 3 failures? Well, that's the probability. Well, the probability of the first hole being a failure is 1 minus p. The probability of the second hole being a failure is 1 minus p. And the probability of a third hole is 1 minus p. So we have to take the product of probabilities to get that. So that gives 1 minus p to the third power. And I'm going to warn you here, this little 3 is going to disappear because I'm actually going back and editing my video. It's going to change into a 1, into an n. So just ignore that when that happens. This should be 1 minus p to the third power. Or the probability of n, little n, successive holes being failures is 1 minus p to the n power. And so just to talk through the reason of why we take the product of these to get to evaluate the probability of 3 successive failures, let's consider our dice again. So what's the probability, for example, of getting 2 failures in a row? 2 failures, and those were heads in a row. So if we toss our first toss, the possible outcomes are a heads and a tail. So we have a probability of 1 failure being 1/2, and in our second toss, okay, it's possible that the head we get is a head or a tail, but it was also possible that we got a tail in our first toss, so there are 2 possibilities with that. And so the probability of getting 2 heads is shown by this possible outcome. And so our second toss had a 1/2 probability of getting a head, and so the probability of getting 2 heads in a row is we have to multiply 1/2 times 1/2. So our first toss gave a 1/2 probability of getting a head. Our second toss had another 1/2 probability of getting a head, and so we had a 1/4 probability of getting 2 heads in a row. So this is an illustration of why we have to multiply probabilities with successive tries, and this is assuming the successive tries are independent of each other. So now let's look at the probability of drilling n holes and getting one success at the end. Our last hole is our success. So here we have the probability of the first n minus 1 holes being failures. So that gives us 1 minus p to the n minus 1. And if our last hole is a success, then we multiply by the probability of that last hole being a success. In the last scenario, let's consider a case in which we have the probability of drilling n holes and getting r successes at the end. And so our first n minus r holes that we drill are cold. So that's the probability of getting n minus r failures. And then the last r holes are successes. So the probability of success of a single success is p, and since we're getting r of them, we have to multiply p by itself, r times. So now finally we're going to look at our last situation, and this gets right at the binomial distribution. So what is the probability of r successes out of n holes? And in this case, we don't care whether the r successes come out, at the very end, or some successes come in the middle, or all of them come at the beginning. So the order of the successes doesn't matter in this case. So we started off with the probability of a specific ordering, that is n minus r failures followed by r total successes. But this is only one permutation out of a number of permutations to get our r successes. So the number of possible combinations of r successes is our combination or our combination equation. And that was written n over r, and the equation is n factorial over n minus r factorial, n factorial divided by n over r factorial divided by r factorial. So that gives a number of ways in which we can get r successes in any order. So the total probability of getting r successes in any order is the probability of one order, which is all the successes appearing at the end, times the number of ways of doing that. And this is our binomial distribution. So for a given n and little p, it gives a distribution of probabilities for all values of r. Oh, and I better delete this little line here. This is not a fraction, it's our binomial coefficients. Okay, so I've written a little script here that calculates the probability for when there are n trials here, and the number of successes goes from 1 to n. And so I'm going to plot the probability for 1 success, 2 successes, etc., all the way up to n successes. And when the probability of a single success, in other words, if you draw it once, the probability of getting a success out of one draw is 0.75. So let me go ahead and, okay, so the way this is coded is, first I have to compute our binomial coefficients, and those are the combinations given n and r, and then I multiply those coefficients for all the possible values of r times the probability of one permutation, which is n minus r failures followed by r successes. And then I'm going to plot a bar plot with the probability on the vertical axis, r on the horizontal axis. And we get something like this. So the highest probability occurs at 15 successes, which is about 75%. That's 75% of 20 trials. And the highest probability, so the highest probability is at 15 successes. If I were to change this from 0.75 to 0.25 and run it, then the highest probability again occurs at 5 out of 20 successes, which is centered on 25%. But it's still possible that even with the probability of a single trial getting a success being 25%, it's still possible that you can drill 20 holes, for example, and get 10 successes. That probability is much lower than 5, but it's still possible. So this shows the distribution of probability of this number of successes given n trials and this probability of a single success. Okay, so that'll conclude this video on the binomial distribution.